The section that we are doing now, bipolar junction transistors, is going to look mostly similar to what we just did, except that bipolar junction transistors work differently. They don't work the same way, but you have to do the same things. You have to put them in a bias circuit. You have to find a Q point. You have to analyze the DC and the AC. So that part of it will be the same. How you do the DC analysis and how you do the AC analysis, well, the DC analysis is different. But then the AC, when we get to that part, is almost exactly the same again. So we have models. We'll go over the models this week. It will look very similar to the 3 weeks we spent in MOSFETs. So, although most people find BJT is a little bit somewhat easier sometimes. The difference between MOSFETs and BJTs, the big difference, is that with a MOSFET, you have no interaction between what's at the input in DC and what's at the output. So in other words, since there's no current that goes into the gate, and it's the gate voltage that controls the output current, you have to use this, solve the quadratic equation to find the drain current, because there's not a direct relationship between what's happening in the input. It's a little more complicated. With bipolar junction transistors, there's just a direct conversion from the input current to the output current, and that makes it a little bit easier. It's a value that's found in the spec sheet. So we talk about that. We will cover all that. But first, we are going to cover bipolar junction transistors and how they're put together. The bipolar junction transistors are basically 3 semiconductor regions. You either have an N, a P, and an N, or a P, an N, and a P. So there are only 2 different kinds that you have to deal with. It is a 3-terminal device, just like a MOSFET. The collector is similar in location to the drain on the MOSFET. The base is similar in location to the gate, and the emitter is similar in location to the source. The difference is how they operate. So there are 3 terminals. They're going to look the same when they're in a circuit, but how they actually operate and affect the circuit is going to be a little bit different. Most of the current flow is between the collector and the emitter, and the base current controls that current. Unlike the MOSFET, which was the input voltage, the gate to source voltage, which was determining what the drain current was, in a bipolar junction transistor, the base current determines the collector current and the emitter current. And the emitter current and the base current, the emitter current and the collector current are not the same. Remember, in a MOSFET, the drain current and the source current are exactly the same current because the electrons are just going through the channel, and it's not the same in a BJT. It's more complicated. So the actual current is not the same in the collector and the emitter. It's slightly different. The emitter is the most heavily doped region. There are actually variations in doping that make this work. So the emitter is most heavily doped. The base is sort of just medium heavily doped, and then the collector is least heavily doped. So they usually differ by about a power of 10. So the collector might have a doping concentration of 10 to the 15, and then the base would be 10 to the 16, and the emitter would be 10 to the 17, and it would kind of work like that. So this is a very simple picture of what an NPN transistor would be. There are 2 PN junctions. There is the emitter-base junction that is between, obviously, the base and the emitter, and then there's the collector-base junction that is between the collector and the base. So as you can imagine, both of these regions are going to have to be biased properly. One of them is, they can either be forward or reverse bias. So actually, you can technically come up with 4 different ways to bias the junctions, although one of the ways is never ever used or encountered, so there are actually going to be 3 that we use. You will notice that the N-type has a plus, which means it's very heavily doped, and then the middle part, the base region, has just a plus, and then the collector region has no qualifier. A PNP looks pretty much exactly the same, except that it has P and N and P type. And the only real difference that we find is that the currents go the other way, which is the same as when we talked about PMOS. PNPs are not quite as complicated as PMOS, because all you're doing is reversing directions and current and voltage polarities, whereas with the PMOS you had to remember whether to use the absolute value of something or an actual number, and with PNPs it's just everything goes the other way. That's really the only big difference. So there are three ways that you can operate depending on the bias conditions of the two PN junctions. Remember, I told you there was one that's never used. And these would be the three different modes you can get. In a BJT, saturation means something different than it does in a MOSFET. So saturation mode is not what we use for amplifiers. We use what we call active mode. And actually in a MOSFET, the saturation mode is also called the active mode in a MOSFET, but in a BJT, the active mode and the saturation mode are not the same. I was not in charge of making up these names. Someone else was, and they evidently decided that saturation would be a good word to use with a MOSFET, since MOSFETs actually came after BJTs. BJTs were actually modeled after tube transistors, so they technically came first and got the word saturation, and then the MOSFET just used it. In fact, there's a lot of unfortunate terminology in MOSFET. Saturation is one and pinch-off is the other. So we can blame the MOSFET people for that. So if you have both junctions reverse biased, that's known as cutoff, and that basically means nothing's happening. It's not on. The base emitter junction would be not allowing current to flow. The collector base junction wouldn't be allowing current to flow, so nothing happens. In saturation mode, both junctions are forward biased and you get the maximum current you can have, but you can't amplify anything. It's not going to be good for an amplifier. This basically, going between cutoff and saturation, is when these transistors are used as switches. They're just going back and forth between cutoff and saturation. Active mode, we have the emitter base junction forward biased, and then the collector base junction is reverse biased. And the fourth way one could do this, we could reverse bias the base emitter junction and forward bias the collector base junction, and that is called reverse active. I have actually heard that term used in a book. But if you go and put that, basically this is what happens when you put your transistor in your circuit backwards, and it does not respond the same way at all. Basically, it doesn't do what you want it to do. So that's really not counted as a proper usage of the device. And the reason that it doesn't work this way is because it's not a symmetrical device like a MOSFET. MOSFETs are very symmetrical, and these are not. They have a different doping concentration for the emitter and the collector, so you can't switch the emitter and collector and have it work the same way. So three modes we worry about. Active mode is what we use for amplifiers, and you'll find that it all looks very similar to MOSFETs once we kind of get around to talking about what the devices actually look like. But first we got to talk about what happens in active mode. So active mode is what we use when we want to amplify a signal. And when we have active mode, we apply two bias voltages, and this would be an NPN structure. So you notice that the P region is in the middle, and the values of current moving, this is why current flow is a little more complicated actually in BJTs than in MOSFETs. In MOSFETs, you just have current moving through a channel, and then the channel eventually closes at one end, and that limits the amount of current. And it's the same current flowing through one into the other. In a BJT, it's a completely different process, which I will explain because you're engineering students and you should know what this process is. I do not expect you to repeat it back to me because I certainly couldn't, as a student, repeat it back. But I can tell you kind of where the components of current come from and why the emitter and the base current are not, or the emitter and collector current are not the same. First of all, there are two bias voltages, so the base emitter junction is forward biased, and the collector base junction is reverse biased. So we got that going, and then something will actually start happening. So what ends up happening is there are majority carrier electrons in the emitter, as you can see labeled above where it says injected electrons. The term injected means that they are forced. They're being forced by the voltage that's being applied. So because you have a negative charge at the emitter, it's pushing the electrons away. So it's pushing electrons into the base region. They're majority electrons when they are in the emitter region, and then they move to the base region and they become minority carriers because now they're in the base region, there's lots of holes, there's only a few electrons. And some of those electrons that have now gotten into the P region, some of them combine with the holes because there's tons of holes and there's just a few electrons, and some of the electrons combine with the holes, and so some current will flow into the base to replace those holes because there's holes being lost. So the base current flowing in, part of that, not all of it, but part of it, which is labeled IB2, part of that is to replace the holes. Then the rest of the electrons that manage to not recombine with anything just skate on through, they get pushed on through to the collector region and they become majority carriers again. So you get majority carriers moving and being minority, then back to majority carriers, and that is all the collector current right there. It's all the electrons that manage to get from the N region through the P region and to the other side without recombining with anything. So that's basically the collector current. However, because all currents have to add, we have to adjust for the fact that some of the electrons are lost in the P region. So the other thing that happens is that we have some minority carriers in, we have majority carriers in the base region, and they also are getting pulled into the emitter region because there's a positive charge kind of pushing them. So some few holes go over into the other region, and that makes up the other part of the base current. So the base current is two things. It's electrons that recombine with holes, and we want to bring in some current to replace that. And then there are some holes that gets pushed over to the emitter region, and we need to bring in some holes to replace that also. So the base current actually has two types of current. And the emitter current ends up being the holes that move into the emitter region plus all the electrons that went away. So those two things combine, and that makes up the emitter current. The bulk of all the current flowing is those injected electrons that move from N to P to N. That's the bulk of it. That's a big, big current. What's happening with the base current is really, really tiny. It's just small number of recombined electrons, small number of holes that gets pushed into the emitter region. And the movement of charges is made because the bases have different doping concentrations. So if they didn't have this kind of really heavy doping and then medium and then light, they wouldn't move quite as well. So that's, in a nutshell, kind of how it works. Oh, I still have things that say stuff that I already said. So the emitter current is the net current that we get from the injected holes and electrons moving back and forth. The base current is the loss of holes injected into the emitter and the holes lost due to recombination. So those are the two things that make up the base current. And then the collector current is the current that gets the electrons that have been swept across the base and through the depletion region and end up in the collector. So that's why the emitter current and the collector current are not the same, because they're not the same. Yes, you had a question.
Is there a significant difference between IC and IE?
Usually it ends up being, no, not hugely significant. Say if you, for example, you would possibly have like 2.6 milliamps for the emitter current, 2.5 milliamps for collector, and 100 microamps for base. That would be kind of a range in which you would find it. The base current, as you will see in a minute, tends to differ from the collector current by a power of about 50 to 200. And we'll talk about why in a minute. So collector current, emitter current, not the same current. They're close, they're not the same. So looking at the collector current just by itself, it flows into the collector, obviously. This is still looking at NPNs. PNPs are just backwards from this, and we'll go through them kind of really fast, but it's going to be the same thing. So there is an equation that describes, as you can imagine, the current going into the collector, and it actually looks very similar to the current describing diode current. You should have seen this before, except that we have base emitter voltage instead of diode voltage, and we have collector current rather than diode current. So that's one kind of difference. We notice that the collector current is controlled by the base emitter voltage. You'll see later that we don't usually use that as the controlling factor. We usually use the base current, but to start out with mathematically, we talk about the base emitter voltage. And the thermal voltage is the VT, not threshold voltage. There's no threshold voltage related to BJTs. In general, the way I do things is threshold voltage is a V sub small t, and thermal voltage is a V sub large T. Yes?
What's IS again?
That's the saturation current. And that is the same as what you had with diodes. That's the current that flows, small amount of current that flows in the reverse direction. And that's given to you or found in a spec sheet. The base current is made up of two things. IB1, which is holes injected into the emitter from the base, and IB2, which is holes flowing through the base or into to replace the holes lost through recombination. Both of those are proportional to E to the VB over VT. And you can add those two up, and that gives you the net base current. So now we can start to relate the input and the output, which we were never able to do so easily with a MOSFET, but we can do really easily with BJT. If you have a configuration in which the emitter is common to both input and output, this is similar to when we talked about common source with MOSFETs. If the emitter is, or the common emitter is probably the most popular form in which amplifier circuits are, we could figure out the common emitter current gain as just IC, which is the collector current, over IB, which is the base current. The base current coming in, the collector current would be the output current, and that's related by a standard term known as beta. Beta generally ranges between 50 and 200. Power transistors have lower values of beta. Transistors we use in amplifiers have larger values of beta. And beta is given on a transistor spec sheet. It's listed generally as HFE. We don't cover H parameters in two-port networks in this class, but that's why, because it is actually a type of H parameter that you use in a two-port network, in a hybrid two-port network, which I guess someday you guys learn about that. I don't know. I haven't figured out when that happens. Maybe never. But in any way, you can look it up, and it tells you, basically, if you can figure out the base current, it automatically tells you what the collector current is. So it's not so hard to relate what's on one side to the other side. that you don't have to go this find VGS, find VT, do this, solve this quadratic, none of that. It's very straightforward. The collector current is just beta times the base current. We also, because all laws work, all the basic laws work, the emitter current is just the sum of the collector and the base current, which is also cool. So once you find the base current and you've found the collector current, you can find the emitter current. All the three currents are related and are easy to relate. We can also find the base current directly, or the base current or the emitter current or whatever, by relating the base current to the emitter current by beta plus 1. And that seems like a very small difference, because if beta is 200, it really doesn't matter if you multiply the base current by 200 or 201. You're going to get a very similar answer. But we differentiate it mostly because if we assume that IE and IC are equal, which sometimes people do, then we're saying basically the base current is 0, and it never is. So we usually do not make that assumption. We usually use beta plus 1, even though it's going to be very similar to beta. If we happen to have a configuration in which the base is common to both input and output, which also happens, we can find the common base current gain, and that would just be the collector over the emitter, and we come up with a parameter called alpha. And alpha is the other relatable parameter and can be found if you know beta. So if you can look up beta in a spec sheet and take beta over beta plus 1, that gives you the value of alpha. And alpha is going to be obviously really close to 1, because beta is a large number and adding 1 to it is going to make it be really, really close to 1. Not exactly 1, but very close. So the summary of how all the currents are related is here. If you know these or can use those, you can generally find the currents that you need in the circuit. Oftentimes in configurations, it's easiest to find the base current first, and then once you find that and you know the value of beta, you can just roll right on through and find the other currents. So the DC circuit analysis tends to be slightly more straightforward, I guess, than the MOSFET. All right, so we have these values of alpha and beta. I'm going to go over how PNPs work. This is exactly the same as what I just said, except we just replace holes with electrons and electrons with holes. That's it. So we have mostly doped P section in the emitter, less mostly doped N section in the middle, and then the P section for the collector. We apply the two bias voltages. Note that they're listed a little bit differently. We're listed VEB and VBC instead of the reverse, so everything just gets reversed, and the current directions are all in the opposite direction as before. We take majority carrier holes this time in the emitter region, and they are get pushed into the base region because we've got a positive voltage at the emitter, so the holes get pushed into the base region. They become minority carriers, and then again, some of the holes recombine with electrons in the base, which gives us IB2, which flows, actually it flows out of the base, not into the base. I have to change that. That should be out of. There. Flows. What now? Oh no, it is forward biased.
Forward based.
Oh, where did I get that? Oh, I did. Thank you. There we go. There's always something, you know. But anyway, it's probably like that in the first one too. I don't know. Okay, I'll fix that. No big deal. And then we take the remaining minority carriers. They move to the collector, so the holes go from P to N to P. That's the majority of the current. It's the same direction this time as the flow of carriers because they're holes. And then we get some electrons that get injected into the emitter region because of the or the positive charge on the emitter, and then we get some current flowing in, and we get the same kind of current flow. So now I have to catch up with myself. All right, so that's pretty much the same and the same. All right, so active mode, we determined we have to have forward and biased and reverse biased junctions. Saturation mode is a little bit different. In saturation, the emitter base junction and the collector base junctions are both forward biased. So this means that the transistor is turned on as much as it can be. Basically, it's pulling as much current as it can. And the collector emitter voltage, because the collector current is big, the collector emitter voltage gets smushed down to almost nothing. Basically because whatever resistor you have in the collector is dropping more and more voltage. So as it drops more voltage, it pushes the collector emitter voltage down to where it's about 0.1 to 0.3 volts. Very, very small. And this is what happens then. You can keep increasing the base current, but nothing happens with the collector current. You really can't make more current come out. So what ends up happening is the value of beta actually is different in saturation. It's actually forced to be something different. And it's generally, we have to just take IC over IB in saturation, and that gives you the value of beta in that mode, and it will be less than the value of beta given in the spec sheet. So something has to change as far as relating input, output, and having KVL and KCL and all this stuff work. So beta is the parameter that changes to accommodate that value. We have several models, and we look at the small signal models later. We look at the large signal ones first. That's what we did with MOSFETs. And because we have a base emitter junction at the beginning, and it's going to be forward biased, we actually model that as a diode, because that's what it's like, a diode, basically. A base emitter junction that's forward biased looks just like a diode. So we model that as a diode, and then we model the output current as just the relation with using the same almost diode voltage to create that collector current that's coming into the collector. And it's a relatively simple model. We can use that. If we choose to concentrate on the voltage controlled part, then we put VBE in and we use the equation that relates VBE to IC. If we want to concentrate on current control, we put IB in, and then we put beta IB for the output current. And those two models give you exactly the same values at the end. So they work exactly the same way. It just depends on what happens to be your particular focus. You can also look at a PNP model. A PNP model for the voltage controlled source looks very similar. And then I'm just going to do a short example of how to put things into the model. So let's say we have an NPN transistor in active mode. So we know that beta is going to be whatever we say it is, that's what it's going to be. We have the saturation current is 10 to the minus 15 and beta is 100. And the emitter is grounded. The base is fed by a 10 microamp current source, and the collector connected to 5 volts DC with a 3K resistor. And we want to find VBE and VCE and verify that this is in active mode, which means that VCE would be a bigger value than like 0.3, so it would be a normal value. So because this is kind of a word problem and a picture usually works better, we basically are going to use the model, the current controlled model, because we have the value of beta. We do have the saturation current, but basically we're feeding this through a current source. So that's going to make the problem easier if we just use the current controlled model. So then we just add in the other values. We add in the grounded emitter, so that would be the first thing that we put. The emitter's grounded. The base is fed with a 10 microamp current source, so we just put a 10 microamp current source there. And then the collector is connected to a 5-volt DC supply through a 3K resistor. And there is a typo on this slide, so don't pay attention. It says RC equals 30K, and it doesn't. It equals 3K. So there, I'll just get rid of that. So we have that value, and that gives us a picture of the, let's see, hopefully I did that with, yeah, I did. Okay. I was making sure I did the math right rather than just labeling the thing. So we've got a picture, which makes it a lot easier. We can replace 100 IB also and put VCE and VBE in where they would be. So VCE is at the output between the collector and ground, and VBE is at the input between the base and ground. And then we can replace that value of beta at some point with 100. There we go. So now this is the full model. It's got everything that we were given, and then we can just go ahead and figure out values. So we can start with finding IC. We need to turn things around a little bit. We can't really find any currents yet, but we can use the IC equation in order to figure out what the value of VBE is. So we can start with IC as beta IB is ISE VBE over VT. And we can move IS to the other side and get beta IB, because we know IB, so we're good there. We know beta and we know IS. And then we can take the natural log of both sides and move the thermal voltage over, and we get an actual equation that gives us VBE. So we go through and we get 0.025 for the thermal voltage. Remember that usually we use 25 millivolts in here, mainly because room temperature is actually lower than 300K. So if you use 25 or 26, I don't really care. You'll come up with different numbers if you use 26 than 25, but not much. So we end up taking those values and we get 0.691 volts, which is similar to 0.7, which is what you would expect to get from a forward bias PN junction. And then we can find VCE. That's just VCC minus IC times RC, since the emitter's connected to ground. And we don't really even need to find IC because we can use RC beta IB. And when we plug in numbers for that, we end up with 2 volts. So VCE is 2 volts, and VBE is 0.691. So because VC is greater than VB, the transistor is in active mode like we would expect. So this is the beginnings. Yes?
Do you simulate it to get those answers, or did you plug it in? Because I got something at least almost 9% different than your answer.
Which one did you do?
What do you mean? I plugged it in just how you have that.
Did you use 30K?
Huh?
Did you use 30K or 3K?
What do you have to use there? I'm talking about for VBE. You don't use it.
Did you use the first time I did the problem, I used 26 millivolts, and the second time I used 25?
I did 25. I did it 3 times. I kept getting 0.633.
So maybe you have the answer from 0.26.
No, the answer from 0.026 is different.
I was just asking. I don't know.
So go through and do it and see if which number is right. Yeah, everybody take out a calculator and figure out which number is correct.
Bro, you just dug yourself a hole. If we all get the right answer.
Oh yeah, and that's not 30K, that's 3K again. Are you still getting 0.633?
DVE, right?
Yeah.
Yes. You got 0.6 what?
91, what is that?
Okay, you got 0.691. I generally believe Marissa when she does stuff.
Oh, that's weird. I got 0.633.
Okay, there's something. Oh, that's okay. This is interesting.
Is everybody agreed?
Well, it shouldn't matter.
It shouldn't. It shouldn't matter.
No, but I do mine piece by piece. I don't do it all at once.
Yeah, I did mine. Now, one thing to make sure of is that everything inside your natural log is correct, so that you have proper parentheses to make sure what you're doing is correct. Let's see. Isn't that funny?
It's about an 8.7.
Yeah, you know, this is real interesting because I've done it on mine, like I said, and gotten.
Do you do it all at once, like what I did?
I think so.
I do mine piece by piece. Like I do 100 times anyway.
That's really funny. And you have a different but you have a better calculator.
Okay, I do it piece by piece.
What?
So you have to go up and
That is the most insulting thing an engineer can hear. Oh, she's got a better calculator.
No. I have the same calculator. So
Inspire is
Inspire is precise.
Yeah.
I feel like.
and accurate.
oh, I do that. Let me ask you one thing. How many of you are entering 1 e to the minus 15?
I'm putting 1
Yeah, no, mine's obviously 10 times e to the negative 15.
Well, that's not what that is. That's 1 times 10 to the minus 15. It's 10 to the minus 15 or,
I guess what you
Wait,
got.
so
Yeah.
it's even like 14.
yeah, this is a common mistake when you're entering like 10 to the minus 15. People go, oh, it's 10 e to the minus 15, and it's not. It's 1 e to the minus 15.